Hello everyone, this is our Mirobot robot arm project, and these are our members. Our project is called A Blueprint for Low-Cost VLA Research, adapting the WLKATA Mirobot to the lerobot and SmolVLA Framework. The goal of AI robotics is simple: make robots follow natural commands using VLA models, but the reality is these powerful systems are too costly, requiring expensive robots and high-end GPU like the A100. This locks students out. Our core mission was to change that. We set out to prove that small AI models for robotics can be successfully deployed by students for real-world projects. To achieve this, we are using SmolVLA, a lightweight efficient model in collaboration with the open-source lerobot toolkit from Hugging Face. This is our entire workspace. We established this fixed setup to easily record data and test performance. It includes our robot arm, a tiled map for vision, testing cubes and boxes, and both a wrist camera and a top camera. Importantly, we achieved this on a budget. We built our own custom wrist camera and a DIY servo gripper. Our only professional component for vision is the Intel RealSense camera for the top view.
Next, I'll briefly introduce the overall workflow and results of integrating SmolVLA with WLKATA Mirobot. This is our implementation loop. We begin by collecting a dataset, then we proceed to train the model, adjust and refine it, and finally conduct evaluation. After each cycle, we review the model's performance, analyze the causes behind the results, and then attempt to collect improved datasets or further refine the model. During the model refinement stage, we discovered that the Mirobot's inherent mechanical limitations prevented SmolVLA's output commands from being executed correctly. To address this, we designed functional clipper and rate limiter modules to ensure full compatibility with the Mirobot. These components were integrated into the translation layer, allowing the model to account for workspace limitations during training. Finally, I will present some parts of our data collection, training, and fine-tuning process. And this is the original way we collect the data. And then this is our new way, which is more stable. And then this is how we train and fine-tuning.
So here's the example of training and fine-tuning. Here is like some of the dataset sample of stacking. And here is the results of pick and place. And here is another result of pick and place with extra cubes. So it has some distraction on the robot. So the method that we use to have the analysis is that first, each task gonna be repeated 20 times, and each trial will be limited to only 2.5 minutes. And in that 2.5 minutes, the robot must finish the corresponding task. If not finished, then it's gonna be marked unsuccessful. And what do we get from evaluating the results? We get the time to complete each task, like the average, and then the success rate, and the robot movement pattern analysis. And here is the task performance evaluation results. So we can see that in our old pick and place results on those 20 trials, we got 80% success rate. But because of some misalignment on the camera, when we do it again the next time, when we do the pick and place and stack and cubes, the success rate drops into 30% and 10%, which is very low. And for the future work, we want to do a data expansion with drawer opening, pouring to manipulation, and multi-view datasets. And for some model improvement, we want to fix current unstable hardwares. We want to try on another low-cost robot for more generalization and integration with anomaly detection.